Okay, ladies and gentlemen, now we are pleased to welcome Professor Christine Curie as our speaker from the University of Southampton. For this third session of today's workshop, we will have Professor Christine to present about optimization via simulation. And now please welcome Professor Christine Curie.
Good afternoon to you, good morning for me, and thank you very much for coming along and listening. I know a few of you already, but there's many of you here who I haven't met. Firstly, really sorry that we couldn't be in Indonesia giving this and all together, but obviously all plans have been changed over the past few years, and this is just one of them. So what I'm going to talk about today is simulation optimization. So I know Stefan has talked to you about simulation yesterday, and Dia has talked to you about optimization today. So in some ways we are combining these two things together to give you simulation optimization. Please do interrupt me on the way through if you have any questions or something doesn't make sense. I may not be able to see the chat immediately, but I will flick back every so often and try and keep an eye on what's happening in the chat and who's asked some questions. I will try and speak slowly, but if I get carried away, my speed may increase. So please do tell me if I'm going too fast and you can't understand what I'm saying as well. What I'm trying to get through today then in this session, and what I'm trying to explain to you through the slides that I'll be presenting, is firstly to understand a bit about what simulation optimization is and why it's difficult. In doing that, kind of understand the different classes of simulation optimization problems. So I assume some of this has been touched on this morning with Audi and with Dia, but we will go into what the different classes of simulation optimization problems are, dependent upon what your decision variables are and what you're trying to optimize. We'll then talk about different methods for solving these problems. So you have different classes of optimization problems. Each class will have its own way of solving, or a good way of solving those particular problems. There'll often be many different algorithms, but they'll be of maybe a similar type. We will go into some of those algorithms, so we'll understand the basic principles of what are called ranking and selection methods. So as you can tell from the name, ranking and selection methods means methods where you have discrete numbers, or a discrete set of options, and you are choosing between them. You want the one that's the best, so you will rank them and then select what you want from that ranked list. Stochastic approximation methods, these we will look at as well. These are things like stochastic root finding problems, so where you have a continuous decision variable and you're trying to find the best one, but you can't get an exact response to what the system that you're modeling's output is. You've always got noise or randomness added on to that. And then random search methods, these are kind of heuristic methods which you would use to find a good solution. So you're not using exact methods, you're using something which takes into account, say, the structure of the problem. I won't be saying a huge amount about random search methods. I'll be focusing on the previous two in what I talk about today. My plan then for the tutorial is to go through an introduction to simulation optimization to begin with, then talk about ranking and selection methods and stochastic approximation. We'll then have a brief part on heuristic methods such as random search before summarizing and spending a bit more time on the practical exercise. So I put this link, because it's a very long link, in the chat, and I think you've also had it in the joining instructions as well for the workshop. So hopefully you are able to access this. I could just click on it, but you don't have that benefit looking at this on Zoom. The link will take you to a Jupyter Notebook that you can look at and work through, and we will come to that during the tutorial. So I will do some talking, we'll go and look at the Jupyter Notebook, and you can make changes to the Jupyter Notebook, run things in the Jupyter Notebook, and test out different ideas, and hopefully that will help with understanding the concepts that I've just talked about. So that's my plan. I think I've got 2 hours for this first session, which is far too much time for you to listen to me for. So I will have some breaks in that, just like Stefan did yesterday. And so we will probably have 5-minute breaks every now and again when I get to a point where there's a natural time to stop. So, and after that, I think we have a longer break, and then we've got a little bit more time after the longer break as well. So we'll gradually make our way through this material, and I will try and send my slides over to someone at the end. I think I've emailed them off to somebody, so we will try and make sure those slides are available to you at some point afterwards as well. Introducing then simulation optimization. So you're going on a very, those of you who only saw simulation yesterday, it's a very fast journey to kind of go through simulation yesterday and straight on to simulation optimization today. So we are going thinking about the fact and what makes the optimization difficult in simulation optimization. What we're looking at then is the post-modeling part of a simulation project. So you've done, and what Stefan talked to you yesterday about with agent-based modeling, you were building your simulation model. And there are other ways of building a simulation model as well besides agent-based modeling. But you have a simulation model which runs and outputs some results for you. Now, one of the key things about the simulation models that we're looking at and talking about today is what they output is stochastic or random. So you have some randomness inherent in the process. And what you're wanting to do is say finds the best answer. Now, you can't just run that simulation model once and with each of the solutions and say the one which is better is the best answer, because you have the randomness in there. Perhaps one of those systems got lucky and performed much better, but it wasn't that the actual system was good, it was just that they had a good set of random variables. And this is what makes the simulation optimization more difficult. So a few examples of things that we might want to optimize. Well, the first is a situation where we have a small number of discrete solutions. So for example, we might be deciding between several different setups for a factory or a hospital to maximize throughput. So in the hospital case, maximize the number of patients that we can pass through the system and get the right treatment as quickly as possible. Now, in this case, the different setups might be very, very different. So, for example, if we consider the factory case, we might be designing a factory and have, say, 3 different ways of laying out our production line. So I have 3 different ways of doing that, and we want to compare via simulation which one looks to be best. Which one is going to give us the greatest throughput? And so, as I said before, we can't just run the simulation model once for each of those. We want to run it several times until we get to a point where we can clearly see that one is better than the other. And we'll see a few pictures and diagrams in a moment that may help with that. The key thing here is that you have discrete solutions, so your decision space is not continuous. You have system 1 or system 2 or system 3 or system 4, and also a relatively small number. And by small, I mean that you can simulate all of them. So you're not just guessing on some of them, you've got time to simulate all of them, because simulation can often take quite a long time to perform. The next example then has continuous decision variables, and this one comes from, well, the example I have comes from revenue management. So this RM is for revenue management. So this is where you're setting booking limits on flights for an airline. So you might have someone flying, for example, from Jakarta to somewhere like Savannah in Georgia in the USA. There won't be a direct flight from Jakarta to Savannah. Instead, someone will have to fly from Jakarta to, say, Austin in Texas, and then change there and get a flight at that point. So this is the network that we're talking about. What the airlines need to decide is how many tickets they will allow to be sold for that route on the, say, small plane from Austin to Savannah. And so it's a really complicated problem because the networks can be huge. So optimizing booking limits in network revenue management, the reason they would use simulation here is there's a lot of uncertainty in the demand, and so they need to take account of that uncertainty. So we will look at that problem briefly later. The third class then, or the third example here, we'll see in a moment that these also correspond to classes of decision problems, is where we have discrete and integer ordered decision variables. So in this case, we have our decision variables, the things that we are trying to decide what value they should take. These are discrete. So they're not following a continuous, it's not something like time or something like distance, which is on a continuous scale. They're discrete, but they have got some order to them. So the example might be the number of call centre staff on duty. So if you've got staff in a call centre on the telephones, you know that if you add one more person answering the telephone, then you will get a better customer response, but you'll also get a higher cost. So that part of it you understand. What you may not understand is how it affects other outcome measures that you are trying to optimize. So these are three examples of where you have a simulation model and you would then like to optimize to improve the outcome. Now, I know many of you have a mathematics background and feel happier with things being put into equation form, and that's just fine. And hopefully this looks similar to some of the things you saw this morning as well. If we're putting it in a mathematical notation, what we're aiming to do is minimize some output f of x. Now, f of x is a function. We're not saying anything about the function at the moment. It's just a function of x, and x is our vector of decision variables because we're likely to have more than one. F of x is the expected value of a random output. So now we are saying something about f of x. It's the expected value of a random output of a simulation model. And this random output of the simulation model we're calling y of x. Now, for those of you who've done some statistics, capital Y of x, it's a capital because this is a random variable. So tend to use little letters for either instances of a random variable or non-random parts of it, so like the inputs x. In this case, our y of x is a random variable that's coming out of our simulation model. Now, we're interested in the expected value of y of x. So we might find that by taking the mean over lots of different replications, and we would get then a good approximation to that expected value of y of x at that point. So f of x is what we're trying to optimize, and we generally talk about minimizing variables here, but it's easy to switch between minimization and maximization just by adding a negative sign, and you can swap everything around. So the output is stochastic or random. And this makes things either more interesting if you're looking at the mathematics, or more difficult if you're the decision maker trying to actually make a decision. So it means that there's some quite interesting ideas in optimization that need to be considered, and from a mathematical perspective, that does give you some fun problems, but it does make it more difficult to decide which is the best option if you are actually just trying to make this decision. So this, just to highlight, f of x is often used to denote a probability density function in statistics. That's not what this is in this case. This is just a function, which is the expected value of a random variable. What I have then is a few more slides that hopefully explain again what we're trying to do. Now these are solving what we'd call the ranking and selection problems. So in this case, we're looking for the minimum value of our f of x. So f of x is our expected value. So actually what we've got are lots of values of y here. So we've run the system, I think 10 times at system setting 1, run the simulation 10 times at system setting 2, and we've found the mean value. So if you were looking at minimizing this and you've run 10 times, not just once, then you would say system 1 looks like it's the best system at this point. Its mean value is lower than all of the others, and there is a little, but what you can say is there's quite a bit of overlap between this and, say, system 3. So system 1 looks relatively clearly better than system 2, but actually how confident are we that it's better than system 3, and also system 10 over here, which we can't compare very easily because it's on the other side of the chart, but actually is also relatively close. What simulation optimization is doing is telling you or giving you the tools to work out how many replications do I need of each of these, so I can really tell that system 1 is better. And also, how can I focus my replications so that I'm not spending lots of time in this particular solution, which is clearly worse than solution 1 if I'm looking at minimizing, but instead of spending more time on these, say, 3 solutions which are close to the minimum and could potentially be the minimum. So in this particular example, things are relatively clear-cut. As soon as I move to this example, where I've got exactly the same set of mean values for my variables that I'm generating, but I've increased the variance, then it becomes a lot more difficult to see what's going on. So actually solution 1 has still come out to be the best, but you can see if I just sampled it once and happened to get this particular value, I wouldn't have seen that coming out at all. So it's a good justification for sampling more than once if you're trying to decide which option is the best. Also shows you how difficult simulation optimization can be when you're in this high variance example. And so this hopefully gives you some justification for why simulation optimization is important, and also why it is difficult as well. Going back then to our 3 different examples we saw earlier, we can think of we can classify these, and this is a paper from Barry Nelson and Jeff Hong from 2009, which has a nice way of classifying these different types of optimization. So the first one is our setup for a factory or hospital where we have a small number of solutions. You could also put the one that we have just looked at. I've put the plot on the 3rd class, but actually if there's no kind of link between the different options 1 to 10 and your simulation model is fast enough to be able to run with each of these different setups for the system, then that could also be counted as a ranking and selection problem. So here we have a small number of solutions and they're discrete and there's no kind of obvious link between them. The second option is where your decision variables are continuous. And so, as I mentioned before, something that we would call stochastic root finding. So in this case, you have some underlying trend. So that's the blue line. So the blue line might be what's the function without any randomness. Obviously, we don't know what that function is, but if we're putting toy examples together, we might do. So this is my toy example where the blue line is the underlying trend in the data and the red points are what I have sampled, because I'm sampling from this function with error, so with randomness. What you're trying to do then is find this point. So we can see the minimum here is clearly at 5 if we have the underlying trend and we can work out what that is. But if we're just looking at those red points, it's very hard to see where that would be. And so that's another class of system where your decision variables are continuous. And then if there is some order, so if this 1 to 10 was something related to call center staff or some other decision variable where the ordering meant something, then you could use some heuristic methods generally to find the right solution if your decision variables are discrete and they're ordered. So these are the three classes of simulation optimization problem. We'll be focusing on these first two in most of what we do, but I will briefly mention the third one. Certainly the examples we look at are just from these first two classes. What I'll talk about next then is ranking and selection problems. So this is looking, as I said, at this first class where we have a small number of solutions. So going into that into a little bit more detail. The characteristics then of these ranking and selection problems, the first, that there are a relatively small number of feasible designs. So you're comparing a relatively small number of designs. What that means is there's time for all designs to be simulated. So even if you've got a very complex simulation model that takes a long while to run, then maybe the small number has to be a bit smaller than if you've got a very fast simulation model that doesn't take very long to run. Feasible designs are generally assumed to be categorical. So what that means is we're ignoring any structural similarity between the designs, or we're not taking that into account when we're doing our optimization. Now, it's generally better if there is some structure in the problem that you do take it into account. And so these ranking and selection problems are generally for situations where it's hard to see easily at all which one would be better, or hard to see any links between the different options. The methods that you find to solve these problems have two alternative aims, and there are different algorithms associated with each of these aims, as you would expect. So the first aim of some of these algorithms then is to sample each design the minimal number of times to ensure that the probability of correct selection meets a set criterion, and these are called indifference zone procedures. So a few things to unpack in that statement. The probability of correct selection. So what that means is that what's the probability that when I get to the end of running my algorithm, I have chosen the actual best design. So that's the probability that I have made the correct selection at this point. And that's what a lot of these algorithms will be focusing on. What's the probability that I got the right one? And in these indifference zone procedures, what I'm then trying to do is say, I want to have the probability of, say, 95% that I will get the best design. What's the smallest number of times I have to test each of these designs before I'm confident that I've got the best option? The second aim then that some algorithms will have is to say, well, I know I've only got this amount of time or this amount of computational time. So my budget is fixed, my computational budget. How can I best use that by sampling of different designs? How can I best allocate it to the different designs to maximize the probability of correct selection? And that's my simulation budget allocation methods. And we'll look at a few of those today. And actually the group that does quite a lot of the work on this is based in Singapore, so much closer to you than they are to me. So these two kind of competing aims, often this second one wins over, that you have this fixed budget that you need to use up in the best way, but there are certain situations where you really need to be confident in your solution and you have that bit more time, in which case the indifference zone procedures work well. So going back to our pictures of coloured crosses and red squares, what we're looking at is knowing how many simulation runs to make. So you might have these red squares are sample averages, and you'll have a set of crosses as well, or a set of individual runs for each of your options. You are then deciding how many simulation runs should I make, how many extra simulation runs do I need to get to a point where I have the answer. And that's what you're working through with these algorithms. And I know some people prefer to think of this more formally, so hopefully I've given you the kind of overview of what we're trying to do. This is a more formal description. So suppose that we have k greater than or equal to 2 possible designs. Now, I will admit this up front, that in the literature you will see the different designs called different designs, different options, different alternatives, different configurations, and I'm confident that I will use the wrong word at some point. So I try and call them designs all the way through. So you're looking at, say, k greater than or equal to 2 possible designs for your system. But I may also call them options, alternatives, and configurations. So apologies if I call them that in what follows, but what we're really focusing on is designs, and we'll try and use designs all the way through. So in ranking and selection, we're going to call these designs x1, x2, up to xk. So effectively, these x's are our decision variables, and we're wanting to decide which of those, whether we want x1, x2, or xk, or any of those in between, which of those is going to be our best design that gives us the best output. Now, just as we saw when we introduced simulation optimization, we're going to use y, capital Y, to denote the output. Now, we have to be a bit more careful than this when we talk about the output. So we have this subscript j, and that says this is the jth time I have run the simulation with design xi, and this is the observation I got when I ran it for that jth time with design xi. So yj of xi, jth observation, design xi. So this is what we're combining, and we'll offer when we're looking at the results for design I, so when we have that input variable xi, we'll be looking at combining these yj together to see what the mean was and maybe what the variance was before deciding what to do next. So our aim is to identify the design with the minimum expected value for the random output y of x. So we're looking at which of those xi is going to give us the minimum expected value for our y of x. Now, there are two ways of approaching these algorithms. So what we're going to talk about are what's called sequential procedures. It is also possible to look at these non-sequentially, to just do some preliminary experiments in stage 1 and then just run however many replications you need in the second stage. But we're going to focus on these sequential procedures, mainly because they work well. They're also kind of state of the art in simulation. So these are what the top algorithms are using to solve the problem. And yes, I think if you're running in something like Python and your simulation model is in Python, just like the agent Py that Stefan presented yesterday, then it's very easy then to run these sequential procedures. Where it becomes more difficult to run sequential procedures is where you're using a software package, and it's hard then to put your code in so that you're outputting things after every replication and then telling the simulation model what to do. You end up with quite a long-winded process. But if you're using agent Py or some other Python package for simulation such as SymPy, then these sequential procedures work really well. In the first step then we'll initialize our algorithm, and this is true for all sequential procedures. There will be some initialization. This initialization is to run n0 replications for each system. So in this case, as I said, we're working with a small number of systems, so it's possible to simulate each of them and get some results back from all of them. So dependent on what your N0 is, you may already be able to say which systems you don't need to sample again, but generally most of them go forward through the procedure. So step 2 then is to calculate statistics. So what are the statistics of interest that you need to calculate? And those will both be for your output, but also for helping your simulation optimization algorithm work. So typically you calculate the mean and the variance and then do something with those values. But doing something with those values is generally setting for the stopping criteria. So have I worked out what the best system is yet? No. Sorry, yes, I will output. No, I will not output. I will go round again. And what the main routine is doing, what these algorithms are trying to do, is work out how many replications to set for system I. So at this point, at time t, maybe, or the replication t, we're saying, I've gone around this optimization algorithm several times. How many more replications do I need of system I at this point? Do I need another one? If so, I'll run another one for system I, and we'll again check the stopping criteria and go around again and set at each point the number of replications I'm going to make, additional replications to make for each of my systems that are still in contention. So it may be after going around this loop just a few times, some of these systems we stop sampling from, and we're just left with a few that we're choosing between. So I think I've talked for about half an hour. I think what would be good now is to go and have a look at the Jupyter Notebook. So what I will do is I will stop sharing my slides and instead share my browser so we can look at the Jupyter Notebook. So I would encourage you to open it up as well on your machines so that you can look at it as already. So you should now be able to see my browser, which has got the Google Colab in it. Now I will have a kind of pause here and look at the chat to see if anyone is having problems with setting up the Google Colab, and any questions in the chat. So I can see one question already from Suryani, I think. Dear Prof Curry, how does the post-modelling part of a simulation can be designed to ensure a better result? So that's a lot of what we're doing at the moment in the post-modelling part. So this is, you've built your simulation model, you've worked out what outputs are important and which you're trying to optimize. And so you're trying to then design these algorithms to run your simulation in the right way to get a good result. So that's what we're looking at today. So hopefully that answers the question. anyone having problems getting into the Google Colab document? Pop it in the chat. There's a limit to what I can do to help you get in, but hopefully I know a few things that sometimes go wrong that I can help with if you're struggling. I'm not seeing anything in the chat. I'll keep the chat open so that if you do have problems, you can pop it in there and I can help put things together and help sort you out. So an introduction to optimization via simulation. So this is all written in Python, so it's a Jupyter Notebook. And by myself and by Tom Monks, who's a lecturer at Exeter University in the UK. And we put some of this together for a conference, and then I've added an example or two to it at the end. So ranking and selection is what we're doing at the moment, and we'll be looking, and I'll introduce these in the slides in just a moment, KN and KN++ and OCBA and OCBA-M. So what's important to say is about those, the actual code that's designing those algorithms and has got those algorithms running, you can download from this GitHub site. So that's not a very exciting one to run. So what we can do as we go through is run this. So I think I've already run some of this already, but let's run it again just to make sure it's all working. Just like when you talked to Stefan yesterday, this pip install, the first thing it's going to do is to install this package called SimTools, which is what Tom Monks has built. That brings with it various other packages that you will recognize, such as Pandas and NumPy and Matplotlib and SciPy and Seaborn, etc. So you've got a few things coming in with it that will be useful in what you run. I think I'm importing NumPy again. I think that was me being ultra cautious to make sure it's there. What we're doing in this point is introducing what we call some toy models, and we'll talk about these models in just a moment. But essentially they're models we're going to use to test out the simulation optimization. As I say here, we're not looking at generating any particularly complicated simulation optimization models. We're instead looking at any particularly complicated simulation models. We're instead looking at creating models that we can kind of understand, and so we can then really get into what the optimization methods are doing. So our first model that we look at, this called Gaussian sequence model, creates a simulation model where the output of a design just looks like this. What that means is, for example, if we set up this model equals Gaussian sequence model 110, it means that the first option will have mean 1, the second will have mean 2, the third will have mean 3, etc., up to mean 10, and all of them will have variance of 1 and follow normal distributions. So we know already that the lowest value of that is going to be the option 1, the highest value of that will be the option 10. So we kind of know the answer already before we run the simulation model, but that helps us understand the optimization methods that we're using. So there isn't much code to click in this bit, so instead what you've got here is examples of the code and just written about what's looking there, and I'd encourage you at some point to kind of go through and read this in a bit more detail as to what the examples mean. What we will start with then, before we kind of go into these, actually introducing the KN++, the OCBA, etc., is to kind of get a feel for what is going on. So in this part, we're creating some models and exploring them using what we call a manual optimizer. So the manual optimizer is gives you a chance to kind of try putting in these values. So you will see what the outputs are. You can decide how many runs to make with each of the different designs within it. So we're going to use a Gaussian sequence model that I introduced before. So the mean of the first option is 1 and the mean of the last option is 10, and we've got options in between that. And we have a total of 10 designs. So we'll run that. We'll actually just output what it is. So Bandit Casino it's called. It's got 10 designs. Verbose is false. It's not going to tell us lots about it. And what we might want to do, and what, as I said before, what all these optimization procedures will do in ranking and selection is just do an initial set of replications to have a feel for what each of the design points are and what the outputs are. So if we run that, then it will do that. It's already run them. It's not actually told us what is going on, but it's keeping a running mean and a running variance. So we can see now that it's allocated 3 replications to each of those options, and let's have a look at what the means were. So remember that the true means, the underlying means, are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you can see that the means we have out after 3 replications are not so far away from that. So we've got 0.8 instead of 1, we've got 1.7 instead of 2, we actually have 3.0, 4.0, 4.2 instead of 5, 6.4 instead of 6, etc. So you can see it's kind of roughly right. Where it gets a bit skew is here. So this one is 9, its underlying mean. This underlying mean is 8. So actually how the random numbers have fallen out. This one has come out being higher than this one. And if we look at the variances, they should be around 1. Actually, they look smaller at the moment. We've only got a few replications at that point. So what we do here, at the moment, it's set up so it will look at the last 3 designs. So remember, Python starts at 0 and goes up. Its first array entry is the 0th entry, and so its 10th array entry will be the 9th. So that's why it's 7, 8, 9, not 8, 9, 10. So here we've set it up so that it's going to sample designs 7, 8, and 9, which were the 3 best. And we can run with that. Now you could just say, actually, I want 6 as well, and it will run it with all of those. And now if you look at what it's done, it's run an extra replication for these last 4 designs, which could be better. Now if we output the means again and the variances again, you can see that we now have slightly different outputs than we had before. So 7.6, 9, 8.6, 10.4. Actually, this one is still looking higher than that one. And the variances as given. Now, let me unhide these cells. So this is where it's time for you to have a little go. And I think we've got kind of 5 minutes to have a go. So if you've got this open, create a model with random designs. What that means is you don't know in advance that the best one is going to be, the highest valued one is going to be the 9th, the array entry 9. It's got a random set of means, and so you don't know which one is going to be the best. And you get a chance to run as many replications of each design as you think is necessary to make a decision about which design is best. So here we're defining, just contrary to what I did before, we're actually defining best as the design with the largest mean value. So I think I had the smallest before. So this is up to you to do this. So the parameters can stay the same as they are in here, because this will give you your own random Gaussian model. And then you can insert your code in here. So remembering what you did before, and also looking up ahead at previously as what we did. So we could just copy in, let's do our initial set like we did up here and run 3 designs. So we might want to run our 3 designs. We might also want to tell ourselves what actually are the means at this point, and see what's going on. So if we type those in or copy those in, we can see we've run this. This is my particular option. I've run it. This is my code that I've just put in. And I can see that if I'm looking for the highest value, then it looks like this option is doing pretty well, but this option is also doing quite well as well. And so I might then go back and say, actually, I want to simulate those designs in a bit more detail. So I suggest, because we're coming up to, well, an hour since my scheduled start time. I did start a little bit later than that, but it's getting on an hour since you, by the time you've done this, it will be up to an hour. So I would say have 10 minutes looking through this Google Colab, coming up to here, trying some different code at this point to see, and playing around with the different values in these different code excerpts that you have here. So I will start talking again at about 50 minutes past the hour. In that time, make sure you have a little bit of a break and a stand up and a stretch, but also have a look at running some of this code and seeing how you get on with the optimization. Okay, so I will mute myself now, and I will see you at 50 minutes past the hour. So I'll put that in the chat as well. Right, I'm ready to get back again. Hopefully you've managed to have a play with the Google Colab, the Jupyter Notebook, and test out some options and try your own optimization, because I think it's quite important to have a try as well with these things and test out your own methods, because that's what helps you understand what's going on. In the next part of the workshop, then, we'll go into some of the formal algorithms for solving these ranking and selection problems. And the first one we'll start with is the indifference zone formulation. It's slightly tricky to understand, or difficult to understand on a first read, so it takes, although there's only a few lines here, it takes a few more lines to actually explain what's going on. It took me several months to kind of work out exactly what was happening here when I first looked at this. In the indifference zone formulation, then, the best solution is selected with a probability of at least 1 minus alpha, as long as the difference between the objective function values of the top 2 solutions is less than delta. Any solutions within delta of the best are considered acceptable to the decision maker. So let's unpack that then. What it's saying is, I will talk to the person who I am running this simulation for, the decision maker, the system owner, and say, what's your indifference zone, as we call it? If I get an objective function value that's within, say, 10 of the best solution, would you think that was fine? So I might not find you the best, I might find you the second best, but if it's very close to the best, you're probably happy with that. So what's the delta going to be? What's the difference, the allowed difference between the kind of best and second best, where you don't mind if I find the second best? So that's what our delta is giving us. Now, because this is a random process and the outcome I get has some stochasticity and or randomness associated with it, then I can't say I'm definitely going to find you that solution. I have to say with a certain probability I will get to that solution. And that's where the alpha comes in. So in many cases, our 1 minus alpha will be 0.95. So 95% chance I will get you the top solution, assuming that there aren't several solutions that are very good, in which case I'll find you one of them, but not necessarily the best one. So that's what you're aiming for with these indifference zone procedures. And these appear not just in simulation, but also in other branches of statistics and other ranking and selection problems. For simulation, the best known indifference zone procedures have been developed by Barry Nelson, who's at Northwestern University in the USA, and his co-authors. We're going to look at two here, KN and KN++. So as you can imagine, KN was the first one developed with Si-Young Kim, and KN++ was the advanced version where they had corrected some of, well, not necessarily corrected, but relaxed some of the assumptions that they made when they developed KN. Both of these are sequential procedures, and we talked about those before the break. And so they will follow that same general flow through the process as those sequential procedures we saw earlier. In step one, then, just as we saw when we looked at the flowchart, you'll run N0 replications for each design. So you will have a set of designs, and here we define this set I. And I is the set of designs that are in contention, so the set of designs that we are still sampling from. At the beginning of the process, that's all of the designs that we're considering. After running these N0 replications, and it's generally somewhere between 3 and 5 for that initial number of replications, we will find the sample mean for each solution in that set I, and the sample variances. Now, not of the actual designs, actually of the differences between different design outputs, because that's what's important here. So the KN will focus on what's the variability and the difference between these design outputs. Because if you think about it, actually what the absolute values are is important, but it's less important when you're selecting this procedure than what the differences are. Now, once the differences get too big, then we know that one design is definitely better than another design. So we look at it that way. In step 2, then, we will decide which solutions we are going to keep in our set, in our contention set that is in contention, this set I. And we will keep solutions in that set where their sample mean is within some distance of the best, and this gives us a threshold distance. R is the number of replications here, and this WIL of R depends on those sample variances of the differences between the designs that we calculated in step 1. So this threshold is how we decide whether a design is still in contention or whether we've got enough evidence to say that it's no longer important. And then we come to the stopping criterion. So for this particular set of procedures, the stopping criterion is we've got one design left, we'll return that one design. While we still have more than one design left, we'll keep running this algorithm. So if we've got more than one design still in contention, we will make one more replication of the remaining designs in our set I. We will then set the number of replications to R+1, so add one more replication, update the sample means of the designs still in contention, so still in that set I, and we'll go to step 2 and go round that process again. And we will keep going with that until we get to the final point. Now, KN++ follows almost exactly the same principles as KN, as you might expect. It's a builds on KN, but it's designed to be valid when observations are not normal and when there might be some interdependency. So a time when there might be interdependency is when you use a technique called common random numbers. Now, actually, I don't have time to go into the full details of common random numbers today, but essentially with common random numbers, what you are trying to do is to treat every design fairly. So you will use the same random scenarios on with design 1 as you do with design 2, 3, 4. It's quite complicated to actually do that in a simulation model because of how random numbers are used generally within the process. But if you can, and if starting with the same random number streams, for example, then it can reduce the variability in the output. So I won't say any more on that, but if you're interested, it's worth looking that up. It's a well-known technique. KM++ then will follow the same step 1. So we're going to find the sample means and the sample variances of the differences after running our initial replications. Step 2, this red part is the bit that's different. So I think I've also, instead of calling it W, I've called it epsilon. So I've changed the notation very slightly just to emphasize it's a different routine really. But the key part here is KM++ will update our sample variances. So it won't just use the ones that we calculated on those initial 3 to 5, very small number of replications in our initialization. Again, the stopping criteria are exactly the same. What we're doing here is updating the sample means and variances of the designs in contention and going back to step 2. So the key difference is these sample variances get updated in each time step. So I've put here time for some exercises. I'm actually going to put off these exercises a little bit until I've talked about the simulation budget allocation procedures, because it doesn't seem long since we last looked at some exercises. So I'm going to look at the other form of excuse me, ranking and selection procedures and before I go into the exercises, which are all in the Jupyter Notebook again. So simulation budget allocation procedures, these are the other kinds of ranking and selection procedures that we're considering. The aim of these procedures is to allocate more simulation time to designs which are critical for identifying which of the set is the best. So remember what we're trying to do. We're not trying to necessarily very accurately predict what the best answer is. We just want to make sure that we have picked the best design. So generally that will mean we improve our understanding of what the best solution is as well. But we're really looking for those to sample those procedures which we're just not sure about how good they are, but they could still be the best design. In practice, what this means is you tend to spend less time or fewer replications on designs which are clearly poor performers. So we saw that when we looked at the manual optimizer, and we'll go back to that example with these procedures as well. Those designs which are clearly much worse will generally not get looked at again. You will tend to spend more time looking at designs which are close to the best value, but also more replications will be spent on designs which have a high degree of uncertainty. So where you're really not very sure how good this solution is, then you'll also see a lot of replications there. We're going to focus on what's called OCBA, optimal computing budget allocation methods here, but there are other methods based on expected value of information which work in quite a similar way to OCBA. So you may see some of these. OCBA seems to have taken over a little bit, and you see more of those methods out in the literature. How does OCBA work then? So this flowchart gives us a feel for how it works. So the first thing you will do, just as you did with the KN and KM++, is simulate each design for a fixed number of replications n0. So you will do your initialization process, find out something about each of the designs. for each design that you've sampled, you'll then estimate the improvement in PCS. Remember, this is our probability of correct selection that we learned about previously. So you'll estimate the improvement in this if we simulated that design some more. So for each design, you're saying, if I added one more replication for this design, so if I replicated this design one more time, how would that help me in determining the probability of correct selection? And you can kind of see, if you've got a design which is clearly a poor performer, sampling it one more time is not going to help improve the probability of correct selection very much. Whereas if you've got one that looks very good and has got high variability and you're not really quite sure, but it looks like it could be one of the best ones, sampling that one more time will give you lots of information, and so will improve that probability of correct selection more. In the next step, then, you use those results. So you'll sample either the design with the greatest estimated improvement or a combination of those top few in that ranked list. And you will sample those again. And you will then stop after a fixed number of replications. Or you might say, I think my probability of correct selection is this. So they will often estimate this PCS, or probability of correct selection, as they go along. So there will be two possibilities for stopping. Either I've met my computing budget, or I've got to my threshold probability of correct selection. And we'll look at that in a moment, just a little bit on OCBAM. So there are quite a lot of situations where you are working with a decision maker to solve a problem, and the decision maker doesn't necessarily just want one solution. They may want 4 or 5 solutions to choose between, because there are things going on in the real world that you just don't know and can't put into the simulation model. For example, if you're looking at the hospital example we mentioned previously, different systems for running the hospital. Say you have 10 different systems, you might want to look for what are the top 2 systems here, because perhaps one of the members of staff who's there won't like this particular way it's done, or you need to make sure that this fits and that fits, and actually there's some politics involved in choosing. So actually finding a top 2 or 3 for you to choose between is much more appealing than finding this is the best one, you have to do this. So OCBAM, and there are equivalents with indifference zone procedures as well, will aim to identify all of the top M designs using a simulation model. This is called subset selection rather than the straight ranking and selection. So as I said before, it enables the simulation modeler to suggest a set of possible options to a decision maker. And the other place it's used is sometimes as this is being part of a longer optimization process. What you can do with this ranking and selection, this OCBAM, is come up with a good set of solutions that you can then try in some other stage of the modeling. Similar to OCBA, but it's concentrating on the boundary of the subset. So if you think about with OCBA that we just saw previously, you're trying to find the best solution, and so you tend to focus your sampling on what looks to be the best, second, the top few solutions, so the best, second, third best, etc., as you get towards the end. With OCBAM, if you've got a solution that's clearly the best, then you're not actually that worried about getting that one exactly right. What you're interested in is the ones on the boundary. So if, like we wanted to say, the top 5 solutions, the ones you might be sampling would be the 4th, the 5th, the 6th, the 7th. So which side of the boundary are each of these solutions or designs? Okay. So now it really is time for some exercises to test those out. So I will swap back over to my Google Colab. I will show you. This is what it looks like if you haven't opened it already. just going to move the bar out of the way, go back to the one that I had previously. Let's check what's in the chat. I can't read that, so I will ignore that. What we're trying to do here then with this indifference zone Rankian selection is just test out these different algorithms we've learned about. So it starts with Kn, and just as before, click the triangle in the corner and it will import the different methods. So the first import you do is of Kn and Kn++. And we're going to look, let's unhide these cells so we can see what we're actually doing. We're going to look at this sequence of 10 normal distributions, means from 1 to 10 with unit variance, and probability of correct selection. We want this to be 0.5. So this is setting our alpha. So our alpha is 0.05, our 1 minus alpha is 0.095. And we've said within an average of 1.0 of the best, this is setting our delta to be 1. Actually, we set it to be 0.1 down here. So let's say we've set it to be 0.1 rather than with 1. And we're going to follow Law. So Law is the person who wrote the simulation textbook that many people read, and the general consensus is let's do 5 replications for each design. So if we look at what we've got down here, then we've got 10 designs, delta is 0.1, alpha is 0.05, n0 is 5, and we're going to generate our model initially, and then we're going to create this Rankian selection object. So this is basically telling Kn what our parameters are, and these are the only inputs it needs at this point. So I run that, just check it looks right. So it's got this n designs is 10, delta's 0.1, alpha's 0.05, n0 is 5, and we're aiming to maximize. So this is where we can change. If we wanted to, we could minimize at this point. So once we've got that running, we can solve it. So this kn.solve will solve it. And run all the replications we need to get to this point. And we can then do some interrogating on it. So if we run this design, it's going to print out some results. So I've just put a few print statements at the end to get it to print out what we would like. It's going to print out the best design. It's also printing out the allocations. So it will allow you, kn.allocations will give you how many replications were made of each system. What you can see with this is it takes quite a lot of replication. So 874 times this simulation model was run to get to that, what we are guarantee that we've got the right answer. And you can see right up until the end, it was sampling both design 8 and 9, which are actually design 9 and 10. So remember, Python goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the 9th and 10th designs, but indexed as 8 and 9 in Python. And it did come out with the right answer, but it did take quite a while to get there. And as it says, you should see KN simulates the top 2 to 3 designs the most, with the lower performing designs eliminated early on, sometimes after the initial stage of replication. Actually, slightly strangely here, it eliminated these 2 designs much earlier than it did, say, this design, whereas they are in order, so you would expect it to have more in at this end than at this end. But, it just, because of the way the random numbers flow, you sometimes get designs doing better or worse than they might otherwise do. So I would have a play around with this when you, in your own time, kind of look at different values for delta. So if we did have delta equal 1, for example, how would that change it? Just check that it has changed it, and we'll run that again. So setting delta equal 1, interestingly, we end up with very few replications and it coming up with design 9. If we set delta equal to 0.01, I remember one of these breaks it, but I can't remember which one it is. 0.01, then we end up with a very large number of replications here, and it's being very cautious about which one it chooses. So some interesting results. So it's worth playing around with different values of those and seeing how they impact on the results. Now we run km++, does the same thing. We've got our delta. Actually, we still have delta set at 0.01, which is why it's running this for quite so many replications. But what you can see is we're still getting the most replications in those top 3. Total number of replications is actually much lower, I think. So instead of 14,000, as with km, we've got 3,478 here. So this one is an exercise for you, so I won't go through this this exercise. I'll leave that for you to do a bit later on in the process, or afterwards if we do end up running out of time. But I will try and leave some time at the end for you to go through these and for me to be able to answer questions on them. But what the exercise is doing is looking at a simulation model that this time has 100 competing designs, and finding the design with the maximum, the highest mean. And so you can then look at what do you notice about the replications required from each method. So the first part is just setting up the model. When you get to the next part, you need to create these kn and kn++ objects, just like we did up here, and write those in. So this is forcing you in some ways to kind of write the code for yourself and remember how to run it. Exercise 2 looks at a harder problem, and you can see immediately how difficult it is by looking at the mean. There are several values here that have pretty similar means. The best, if we're looking at the highest value, is this 4.3, but the variances are quite different and in actual fact quite high, certainly for the best option and some around it. So you've got a very noisy design. And to look at kn and k++ with the following parameters. What you find is they don't always return that optimal design. Are they returning a design within the indifference zone? Have a look at that. What needs the most replication effort? Is it the same? Always that one that requires the same? And also looking at different values of seed. So seed is the random set of random variables. So this one takes a while, so it takes a few seconds for the procedure to return a design. Imagine what that's like if your simulation model takes 10 seconds or more to run each design. You would be sat there for a long while. Luckily, these are quite simple simulation models. They just take there's just a lot of replications needed. So this will sort it out, and you can then run kn and kn++ to do that. Okay, so I'll go through the OCBA, and then actually I think we'll have a little bit of time after I've gone through your OCBA for you to have a go at doing those and getting those running. So OCBA is what we just talked about in the lectures. This is where you are allocating your computing budget between different designs. So you've got a fixed budget to achieve the best probability of correct selection within the budget that's available. So we're going to import them, first of all, OCBA and OCBA-M, and then we're going to try it on the simple problem that we've looked at many times before now. So 10 designs, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 being their means. OCBA has slightly different parameters. It's got a delta this time, not the same as in the indifference zone. Delta here is the number of replications to allocate at each stage of the process. As before, we'll run our 5 replications to start with, and we'll say we've got quite a small budget. We're only allowed 70 replications. So what this code will do is create our model and run OCBA. Set up our OCBA procedure. So this is just checking we've got the right values in our OCBA procedure, and we'll then find out what the best design is. So if we solve it, it does give us the best design, and looking at how many replications it makes of each design, it's focused very much on those top two to give us our total number of replications being 70. Now, if we run this a few times, we'll see how it gets on. So sometimes it's slow. So we can see it's got 9 again, using a slightly different number. Again, comes up with 9. I think it's quite hard to find it not coming up with 9. I'm going to, no, can't cheat. See that. You can see in this case it did sample the top 3 designs one more time, but mostly it's decided after those initial set of replications that it's happy with what's going on. What I will do is change my N0 to be 3 and see if that makes any difference. So, no, it's not letting. Oh no, there you go. I should have read the rules. N0 has to be 5 or more, so it's not letting you change that to be any smaller. So yeah, quite hard to make this one get the wrong answer, and also quite hard to make it test any of these other options. It's too easy a problem. Exercise 3 then allows you to check that a little bit more. So what we're doing here in this is looking at how OCBA affects the probability of correct selection. So we've got a budget in this case of 75. We've got delta equal to 5. That's the number of replications you make at each stage of the OCBA. 10 designs, N0 equal 5, everything else. What this will do is it will run the OCBA 1,000 times and tell you how many times it got the right answer. So if you run this, it takes a little bit longer because it's doing 1,000 versions of what we've been doing up above. And what this is telling you is 998 times it got the right answer, 2 times it got the wrong answer. So it's a pretty good result. And we can try, as it says, what happens if delta equals 1. You can run it again with delta equals 1. Which is actually, I think, what we had in the previous example, and see what happens this time. Okay, so this time 999 out of 1,000 times we got the right answer. Good. So what I would suggest that you do on this, what am I going to talk about? Okay, let me mention this first before I set you off on doing some examples. We haven't mentioned expected opportunity cost, so I would miss out exercise 4. You might want to look at it later, but I would miss it out because we haven't actually looked at that one. Instead, we did look briefly at OCBA-M. I kind of called that bonus material because it's kind of going one step beyond the basics. What this algorithm is doing is selecting the top 2 designs. So if we run this, we're going to end up with, I know what's going wrong. SVM model. I'm just going to try swapping that round and see if that works. There was a spelling mistake that I think we corrected for some of them, but obviously not for that one. So let me make a note of that. And you can run that. So note that if you do play around with this, you need to misspell Gauss with a U before an A, and print out the results. So and then you can look at selecting the top 3 out of 100 designs, which hopefully doesn't have that same problem. No, because I haven't actually put any code in. Good. What I would suggest then for the next, let's say 10 minutes, is you have a go at working through this code. So you'll need more than 10 minutes to get all the way through it, but just 10 minutes to have a kind of play. So starting right up with the KN, and run through the examples yourself if you need to, but concentrate on doing these exercises. Kind of start by putting a bit of code together. We've run that code to kind of set it up, but putting a bit of code together to create these KN and KN++ objects and run them and seeing what outputs you get. So that's one thing. And definitely having a look at this more complicated model. In fact, we've set up KN for you on this one, so that's got a nice one to look at. Just looking at that, seeing what results that you get out, how it all fits together, and hopefully getting a better understanding. While you're doing that, pop questions in the chat and I will do my best to answer them. Let's say I will start back talking again at about 35 minutes past. So this isn't really a break, this is you going away and doing some coding on the Google Colab. So go and do some coding. In about 10 minutes time, at 35 minutes past, we'll come back and I'll start talking again, and we'll finish off this section and then have a little bit of a longer kind of 10-minute break after I've done my next bit of talking. Okay, so coding for 10 minutes is what we're doing now. I'm going through some of these exercises. And as I say, pop it in the chat if you have a question. Stefan, thanks for passing on that question. I answered it already, I think, verbally. So how the post-modelling part of the simulation can be designed to ensure a better result. That's kind of what we're doing now in the optimization, I think. So once you have done the modelling, you're then making sure you've got the right outputs. And what we're doing now is deciding how you choose then the best system design using the optimization. So this is the part that we're focusing on now. The one thing that we haven't covered are things like warm-up duration and checking outputs in that way and checking that you're measuring the right things when you're looking at your objective function. So that is something else, the output analysis, that may be worth looking at. I'll see if I can find a link to an output analysis tutorial I can put in the chat as well. I've not seen lots of questions in the chat, so I'm assuming that everyone has been getting on okay. Maybe put a thumbs up if you have, as a reaction, if you have managed these to use the Google Colab and you've done some experiments. Not if you've finished it, I don't expect you to have done everything, all the exercises, but just a thumbs up if you've managed to get it working and run a few things with it. That would be useful just for me to know how many people are doing it. So you should be able to find a reaction down the bottom. You can, in the reactions box. So I'm putting a thumbs up now. Just be useful to see how many. Not many by the looks of it, because it's just me with my thumbs up. Oh. Okay. Maybe we'll focus on the slides then, because I can't see any thumbs at all. Right, let's start talking again then, and I will go back to my slides. As I said, so hopefully you use the last 10 minutes to go through and try running some exercises with the Python code that I've given you, although it looks like not many people may have managed to do that if no one is putting their thumbs up. What I will do now then is just briefly introduce the next part, and then I think, according to my schedule, we have a short break at 9:45, so I've got 10 minutes until then. So let me reshare my slides if I can find where I've put my command bar, and we will go back. So the exercises that you've been carrying out, hopefully on the Google Colab, will have given you a feel for how these optimization methods work in practice. So, oh, someone said they couldn't open the G Drive link. Page not found. That's odd because I double checked that link. Maybe the last one I missed off the end of the thing. I will check that for you. So, previously. Okay. So there's a few people couldn't open the link. Let me see if I can recopy the link in there. So you should be able to see the link from here. I will just click on it and check that it's taking me to the right place. So sometimes you will end up with a lot of text. I'll show you what I see at this point. So sometimes you'll end up with a lot of text like this and you need to click open in Google Colaboratory and it will then find it. But this link should work. Link works fine for me. Okay, so it looks like it is just 1 or 2 people who haven't been able to open the link. Hopefully you'll be able to, I'll type it in again, hopefully you'll be able to find it fine in future. Yes, thank you, Audi. That's what I was kind of clicking before. It sometimes ends up with a lot of text. You need to say you want it to be Google Colab. Those of you who haven't found it, when we get to the break, if you still can't manage to find it, let me know, but I'm not sure exactly what I can do. It looks like it is just a couple of people, hopefully. Good. So let me return to my slides. So those of you who've managed to get in there and looked at the Jupyter Notebook will hopefully have had a good play with what's in there. Let me get right to the end, but not quite the end, and use these exercises to test it out. Now, we don't have a huge amount of time today, so I don't think you'll have had enough time to go through all of those exercises and try everything out. I've deliberately given you more than there would be time available for, so you can go away and try these things out later if it's something that you are interested in or think could be something you could use in a project you're working on. So please do use them for that and use them to test out the different methods and get a good understanding of the methods, because that's what we're aiming for. What we're going to be talking about next, and I'm going to start introducing this now and then we'll carry on after the break, is stochastic approximation. And if you remember back to the introduction to simulation optimization right at the start of my session, we had this picture, which is explaining what we're aiming to optimize. The blue line is an underlying trend or an underlying function, but we can't take measurements of exactly that underlying function. We have that underlying function plus some randomness. So what we actually see when we run our simulation model at different values of x are these red squares. Now, stochastic approximation is a method that will help you decide, after you've taken, say, some of these design points, you've got, say, 10 design points and you've got some results, where do you focus your simulation next? So where do you move to? And that's the method that we'll be looking at for most of the rest of the session. There is a little bit at the end on heuristics, but in essence, this is the other method that we're looking at today. So lots of maths on this slide. Essentially what we're doing here is optimizing a function where the inputs x are continuous variables. And we have a set of continuous variables that might be time, it might be length, as I've said, it might be the rate at which something is performed. Whatever those inputs are, they are continuous, and we want to find the minimum of a function that takes those as an input. So we have a stochastic function, we've got these inputs, we want to find the minimum. Essentially what we're doing are what's called steepest descent algorithms, or gradient-based optimization in some ways it's often called, in a stochastic setting. So you can think about this if you can go back to what you studied at school. You have a function which has a minimum value in there, and you will find the point where the gradient is equal to 0. So essentially you're following the gradient down till you get to that minimum point. What we're doing here is a bit harder because we obviously don't know what the functional form is. We don't know the equation for this line we're setting, and we also can't observe it directly. We're observing it with some noise or some randomness attached to it. We're aiming to minimize then the expected value of our random output y of x. So here, remember before our x was our set of systems, we would have x1 was for a set of designs, x1 was design 1, x2 was design 2. That's not the case here. In this case, x can take any value in the allowed range, and we're just finding the one that finds the minimum of this expected value of y of x. So one of the popular algorithms for solving this is the Kiefer-Wolfowitz algorithm, which I think dates from the 1960s. So it's a very old algorithm, but works very well. There have been additions to it and modifications that make it faster or change different bits, but in essence it's remained pretty much the same since the 1960s. Just like we had before, this is a sequential procedure, but sequential in a slightly different way. What I mean by sequential, and in general what's meant by sequential, is we will run a simulation, get some results, and then decide what to do. So how many replications to make. And so in this case, well, in the first case with the OCBA and KM++, it was how many replications to make at a different point. With the Kiefer-Wolfowitz, the sequential part tells us where to place our next observation. So we will run some more observations, we will look at the answers, and then decide where to place our next observation. And this is how we do it. So we have the n+1th data point, xn+1, will be sampled at this particular value. So it'll be sampled at xn, that's where we were before. But then we will look at calculating what the gradient, or estimating what the gradient is at that point xn. And to do that, because we can't differentiate this stochastic function, we're looking at estimating it numerically. So we're saying, okay, I'm at point xn. If I go up a little bit, where my little bit is cn, and down a little bit where my little bit is cn as well, I'm going to run my simulation just a bit higher than xn and run my simulation just a bit lower than xn and find the difference and divide through by, in this case, 2cn, because that's the difference in the x's. And that gives me my gradient. So what's in this fraction here is the grade, my estimate of the gradient at the point I'm at the moment. And we know if we move in the direction of the gradient, we'll head to, well, the negative of the direction of the gradient will head towards the minimum value. This an here is scaling this. So it's saying, well, I don't necessarily want to move a long way. And actually, the closer I get to the optimal value, the smaller the distance I want to move. And so this is why our ANs get set here. And I think AN generally 1 over n, CN 1 to the n to the power of a third seems to work quite well. I have seen 1 to the n power of a quarter as well. So you've got some fractional power of n dictating how big this CN is as well. So it's saying I'm going to get a bit more accurate with my calculation of the gradient, or look a bit more widely as I go through. And you might want to play around with some of these values out the front, and you may want to add constants to them. These are just the their dependence on n, where n in this case is the number of replications you've made, or the stage, well, and more like the stage you are at in the optimization process or the algorithm. So that's the general kind of maths. With this one, I put the maths first and the pictures second. So we'll go through the pictures, and then I think we'll have a little break. So when we're looking at Kiefer-Wolfowitz and visualizing Kiefer-Wolfowitz, this is what we're doing. So we might start at this point x1. We're aiming for the minimum. This is our underlying function, this black line. And the blue crosses are the observations that we see. So actually this doesn't look like it's particularly variable at this point. So I'm at point x1 and I will calculate my just down a little bit and my just up a little bit values and find the estimate of the gradient. And this red line will be the direction that I will travel in, and the algorithm will push me in to get towards my next point. So I'm actually going to end up, we'll say at this point x2. So I've moved along here. This is where I've ended up as my next point. I've kind of moved along a little bit here. So A1 here is my the amount I will multiply that gradient by to move in that direction. So I've got to x2, and at x2 I do exactly the same. I go up a little bit and down a little bit from x2 and calculate the output the values, which are my blue crosses, calculate the gradient. I know I'm then going to move in this direction by an amount A2. So I'll move along to point x3, where I do exactly the same. So these two new points, they give me this direction, and I will move along, make it closer to this true optimal value theta. And there are various, and this is what makes this method quite scary. It's convergence quite defined for the Kiefer-Wolfowitz algorithm, that you will eventually get to that point. What we've looked at there then is in one dimension. As soon as you move into a higher number of dimensions, the difficulty with this algorithm becomes estimating the gradient. And this isn't something I'm a big expert on, so I'm not going to say a huge amount about it. But there are clever methods. I think simultaneous is the method I have heard of, in which you can calculate the gradient just by sampling 2 points rather than sampling one for each dimension of the problem. And that's where a lot of the work, I think, has gone, is in how you get how you efficiently know the direction to move in, and then gradually get closer to that optimal value. These kind of algorithms are used quite a lot in machine learning and these areas, so they're worth looking at to go beyond the simulation, as well as looking at it from a simulation perspective. Okay, the reason I wanted to introduce that now was we're going to have a 10-minute break at this point. So we'll come back at 0:00. I think it's 4 o'clock your time, 10 o'clock our time. So 10-minute break. In that time, if you want to go and look at the, well, I'd encourage you to go and get a drink, stand up, stretch, etc., and wake yourselves up. But if you do all of that and you have a few minutes at the end, then we can then go to the Google Colab and we'll look at some of these examples. There are some really horrible optimization problems at the end of those that are really quite thorny and difficult to solve, that you can have a play around with. That's what the exercises in this particular part are. But just have a kind of look through and see what's there. I'll start when we come back with going to that Google Colab and running through some of the examples there, so we can see how the method works, and how we get on, and then we'll go and talk about the remainder of the work at that point. And I think we should finish. I'm due to finish, I think, around just before 5 o'clock your time. I think we'll easily finish at that point, and there should be time for questions at the end as well, as to how to do this practically, or just anything you have that you want to ask about. For now, though, let's take a 10-minute break to 10 o'clock. I will stop sharing at this point, and I'll pop that in the chat. Excellent. I am back. I can't see whether everyone else is back, but because I don't see pictures, but hopefully you're all back. Gio's back anyway, and Stephanus is back, and see a few people coming back and logging back on. So we are going to have a quick look at some examples, and then we will go back to the slides, and then there should be lots of time for questions at the end. That's my plan before we finish up. So let me share now my screen again, and we will look at the tutorial, the Jupyter Notebook tutorial again. So hopefully you all have something to drink, had a little bit of a break, and are feeling refreshed at this point. Although I'm conscious it's the end of a very long day for you and a long 2 days. So we are looking now at this stochastic root finding. So hopefully you can see my screen and see what I am sharing. So looks like I'm sharing the right thing. Let me just double check I've got the right thing shared. Yeah, okay, all good. So stochastic root finding is what we're looking at now, and that's what we introduced before. So we're finding the minimum of a function that has a stochastic output or some randomness in there. So the underlying model may be simple, it might be complicated, but we don't really know what's going on. In essence, we have a continuous variable, this is our x, and we're trying to find the best value for that x. At the moment in this tutorial, we're only going to look at single dimension problems as they're easier to understand and also faster to run. I did put here, I wrote this bit, so the code looks much less professional, I'm sure, than Tom's part that he wrote previously. He'd put the packages together for the previous part. We're going to look at an example that is just a polynomial example. So the underlying function is a polynomial, and you can look at this function, you can use your calculus and find what the optimal value should be. We're aiming to find the minimum value, and we're restricting the range to between 0 and 2. If you plot this on a wider range, you can see why. Because it's a cubic function, and when the x, or in this case it's written as z in the definition of this poly function in the code below, if you look at what happens is that z tends to minus infinity, you can see that actually that z cubed term will dominate, and you'll tend to minus infinity, assuming d is positive, of course. So I spent a little while kind of putting this function together so that finding the right values of a, b, c, and d, so we have this nice minimum in this range between 0 and 2. So we're going to restrict our search to between 0 and 2. What the code will do here then is it will set up this poly function. So we've given it these particular parameters, so a minus z plus z cubed, so we've not got a z squared term there. Our sigma equals 0.1 indicates how much error we have on the output, and I've set this at 0.1 at the moment. That's the standard deviation on the output. The code will then plot the function for a particular set of x values and output those. So you can also, and I've commented this out at the moment, if you want to check what the output is for just one value of x, run the following code, and confusingly said y equals polyfunction of x, which is, yeah, no, that makes sense. So y is the output at that particular value of x, and you can print that out. At the moment, we're going to print out a set, well, this function for I think 1,000 or maybe 100,000 different values of x. No, 100 different values of this x value, which is spread evenly across the space. And so you can get a reasonably good idea of the shape of this function from that. So it's got quite a steep gradient out of the minimum value and quite a gradual gradient on the negative side of the minimum value. And what you can play around with here is you can just change, if we change our sigma to 1, so we have a much higher variability, then you can see we could end up with something that looks quite different and a lot harder to see the underlying function there. So we will make things easy for ourselves initially and stick with this relatively low value for the standard deviation. So we get something that looks like this. So that's the function that we're minimizing, and we do know the answer to this one because we've set up the problem so that we know the answer, so that we do know it should be at, I forget, 1 over the square root of 3 is where we should be looking. That defines the function we're trying to minimize and shows us what it looks like. What we now need to do is write the code for the algorithm for finding the minimum. And this is where we use the Kiefer-Wolfowitz algorithm that we developed previously, because that doesn't involve knowing the gradient. We're estimating the gradient numerically. Again, we've restricted the range of values that x can take, just because we don't want to if we get down below, I think it's something below 0, there's a maximum here, and then the function goes off down to -infinity. We don't want to get into that space. The first time I ran this, I kept getting minus something very high, and it would tend off to something. I thought there's something going wrong here, and then realised what I was doing. So that actually we do just want it in this small range. So of course it is doing the right thing. It's just me not expecting it to. So here you can see all the details of the algorithm. So that's what you couldn't see with the KM++ and the OCBA previously. You couldn't actually see what was going on inside those functions. Here you can actually see what's going on inside the function. And you have got some initialization. So what are we setting up? Here is my just getting everything in order. And setting up at this point, you can see my AN. If you remember, my AN is how the way in which I scale the gradient when I'm moving to the next point. And my CN is how far out I go to calculate that gradient. So how local I am in calculating the gradient. And so AN typically is 1 over n, CN is typically 1 over n to some power. And I've put that as an input for the function. You can decide what power that you have. If you want to look at what the ANs look like as you go through the process, then you can print those out. And then a few test functions. So this is just dependent on, there are 3 test functions it's set up for. And if the test function is the polynomial one, that's the one we've introduced before. Then when you're looking at calculating that difference, so remember when you're estimating that gradient, you calculate the difference between the high value and the low value. Then at that point, if you're using the polynomial, you will use poly function to do that, with the x that you're looking at being this x plus cn, and then in the one you're subtracting, x minus cn. And so you're getting that difference worked out. Now, there are 2 other functions called nasty sign and another nasty sign. So it looks like nasty sin, which is not really what I'm after. This is a sign function, not a particularly bad act that someone has carried out. So these are other test functions that I've set up below, and we can have a look at those. What the function will do then is it will calculate here what the difference is, and then we'll convert that into a gradient. So this is the equation that we've seen in the slides, the one that I've highlighted in blue. So your next value, your n plus 1th value of x, will be the nth value of x minus an, which is our kind of weighting function, times this difference we've just calculated up here. So the difference between the 2 function values divided by 2cn. So that difference over 2cn gives us the gradient. And so that's how we're moving, or our estimate of the gradient. That's how we're moving around the space. and at the end of the process we'll return that whole kind of set of x's. So we're setting up the parameters again. This is for the polynomial, and we are running this test. So this is what we're doing here. So these are the parameters I want to run. It's just easier to have them nearby. And this is the test. Now this low xkw and high xkw set the range over which I'm looking. And if you have this somewhere less than too low, then you'll be heading off to the lower end of the range, as I've said before. Okay, and then we can plot the progression. So if we run this, what we see as we go through is how the solution moves from 0, which is the initial value, and gets closer to that final value around, its final value is around 0.56, which is pretty close to what the actual value should be. And so you can see we have a little bit, it's hard to spot because the dots are quite small, quite big compared with the fluctuations, but initially we have this kind of fluctuating around the actual answer we want, and then we kind of settle down to a final version. When you test this out, so the first thing to do is try it with different values of sigma, and actually we can just try this again. So remember when we plotted it with sigma equals 1, it was much harder to see what's going on, and actually you can get that out. So we're still ending up in roughly the right area, 0.55-ish, in the right kind of space, but this variability means we're doing a lot of searching early on, and actually something strange is going on here. It's kind of sending it, well actually I think it might be sending itself off to the right value. So there's a lot of fluctuating, and we can end up kind of stuck in the wrong place because of how the random variables have worked. The other thing to try is to try it with some different functions. So I'm just going to run this. Whether this allows me to actually see what these functions are. So, and you can't actually see what these functions are. It's worth having a plot of these functions at some point. Both of them involve a sine function, so they've got some, it means they've got more than one minimum value within the space, but one of them is lower than the other. So effectively they've got local minima. So they're quite nasty functions to choose. What you can see, particularly with the second one, is depending on where you start the process, you will end up with a different answer because it will get stuck in some of these local minimum. So that is worth testing out. That I will leave for you to do probably as after the tutorial work, but something to think about in terms of setting your AN, setting your CN, and also setting your initial values. And that's probably a reasonably important point, which I assume you may have learned a little bit about this morning and in the rest of the workshop, is when you're using these methods, often it's good to start with different initial parameters and see if you get different answers. The reason being is you can quite often, if you've got a nasty function that has several minimum values, and so some local minima and then a true global minimum, it's sometimes easy to get stuck in those local minima. And I think that's what happens here with these sine functions. So maybe what you need to be doing is setting, doing a little bit more, starting at different values, or doing a bit more exploration early on. So I will leave that now, unless there are any particular questions on that example, those set of examples really, and leave you with these ways of getting closer to your optimal value, and some things to test out. As I said, this is quite an old method. There have been more recent methods, and there's certainly things to read around this if you're interested. So I will leave that there, and I will move back to my slides. Let me just check, actually, before I do that, there is one question. my current understanding is on the right path. So is this a method of optimize the setting of a simulation model? Yes, that's right. So you are looking at, you may have a system. So for all of this is true for all of the simulation optimization methods we've looked at. You may have a system that can be designed in different ways. So it might be, so for the ranking and selection methods, that you can design it so people move this way through the system or that way through the system, and you want to pick which one is best. And you use the simulation model to decide where what the setting should be for that. So you'll test it with this particular setup for the system and another setup for the system and see which one works out to give you the best answer in the simulation. And you hope, if your simulation is a good description of the underlying system, that will tell you which one will work best in the real system. In the methods that I've just introduced now, where you've got a continuous variable, a continuous output, or a continuous input, sorry, you are trying to decide what input value will give you the best answer. And it will give you the best answer on the simulation model. And hopefully, as I say, if the simulation model is a good description of the real system, that answer is likely to be a good answer for the real system as well. So effectively, you're experimenting with the simulation model to save you having to experiment with the real system. Because in many cases, experimenting with the real system has lots of cost and implications, or can produce, things go wrong and you do the wrong thing. You could cost the company some money, or the government some money, or people could suffer as a result. So best to test it on the simulation model, find the optimal value there, and then translate that into the real system. So hopefully that helps, Audi. So a question from Fadley: do we have to do data validation before running the optimization modeling? Yes, so it's always good to validate your model before you run the simulation optimization. So that's certainly true. And just check that the output of the simulation model is doing sensible things. The other thing that we haven't talked about much today is the way you set the parameters in the simulation model, so that you're using information from the real system to set those parameter values. And that's also really important, to make sure that your simulation model is telling you the right thing. Because if your simulation model is not a good description of the system, then you can have a perfect optimization model on your simulation, but you don't know for sure that what will work well on the simulation will work well on the real system. So you need to be fairly confident that the simulation model is a good description of the real system to make it worthwhile doing these simulation optimization methods. So hopefully that helps. The use of statistics would improve the simulation optimization method, approximation method. It might do. I don't know that you're effectively using some of these anyway. The problem with calculating statistics is they involve running the simulation model, and that can be costly if you've got a very complex simulation model. So what this is aiming to do is carry out the minimal number of simulation runs that still gets you to a good answer. So it's trying to be very efficient with the number of runs that you make. I may not have answered that question entirely correctly, but so let me know if I've misunderstood what you've asked. But you would, in essence, not calculate means and variances at this point. You would just kind of test out at different values until you got to the right point. 2 thank yous. Okay, that's good. So keep going with the questions. I will go back to the slides now, but keep putting them in, because I will have time to answer more later. And no question I don't believe in silly questions. If you don't understand something, it's quite possible that lots of other people don't understand it as well. I've probably just not explained it well. So please do put questions in, even if you think that they sound silly or so forth. No question is silly. So please do ask anything you don't understand. Okay, just a quick example of this. I'm conscious this is an kind of put this as an aside because it is an example of where stochastic approximation is used, but it's not a standard use of or a common use of simulation. Often simulation is used for solving kind of process problems or some of the interesting questions that Stefan talked about yesterday with agent-based modelling. So in some ways this gives you another idea of how simulation could be used, and it also gives you some real experience of how this stochastic approximation might be used. So the example comes from optimizing booking limits in network revenue management, and I talked a little bit about what that meant earlier, so I won't go into that again, but essentially you've got a network that looks like this picture, a very big messy flight network, somewhat disrupted by COVID because lots of these flights aren't running. But in essence, if you're trying to get from somewhere over here to somewhere over here, you will quite often take a flight to a hub. Well, you may take an initial flight to a hub, which is up here, and then you take another flight to this hub. Impossible to see where these places are because there's so many blue lines, before taking a smaller aircraft out to your final location. So this is the network, and then the question is how many seats can I sell on each of these flights to these particular kind of itineraries or journeys. And this is an operations research paper, which has got quite a lot in it. So I'm not going to go through this in a huge amount of detail, but I did want to talk through the general principles because I think it's quite interesting to see how stochastic approximation might be used on an example like this, because it breaks some of the assumptions of stochastic approximation. So we say BT is our set of booking limits that are used in time period T. So remember, with an airline, you have a booking period in each time period of your sales. So you might be selling these tickets for 100 days, and in each of those you will have okay, in this booking period I'm allowed to sell up to this number of seats in this particular class. So the class corresponds to the price and also the product that you're selling. And then the authors make define a couple of quantities. So QT with this little q is the revenue generated in period T when you have used these particular booking limits, and the capacity that you have remaining on your flights is this CT. Whereas big QT is the total revenue generated between now and the end of the booking period, so when the airline flies, if you set these booking limits to be BT in period T, and then pick the optimal booking limits after that. So for each start of each time window, the airline wants to maximise the expected revenue in the remaining time periods, because its aim is to maximise its revenue. So it will look at how it should set its revenue up until the end of the time period. But really what it wants to do is, what's my booking limit that I should set now? And the expected total revenue is going to be this expected value of QT when I've set these particular booking limits, which is going to be what I get in this period plus what I will get if I do the optimal thing in the next period and keep going onwards. So this RT is just this QT as well. So the authors, to do this, simulate the revenue that receives. So they've got a simulation model that's saying, okay, this number of people are going to show up. So I'll generate a random number to say this how many people are going to show up, and this is the probability they'll buy a ticket at this price, etc. And we can use that to estimate what's the revenue we'd get in the rest of the time period. And that means we only really have to look at this value when we're doing the optimization. Now, the one assumption they break in the stochastic approximation is they assume that booking limits are actually integer. So rather than continuous, so we'd assumed that we had continuous variables, but actually they are integers. So but what they're doing is kind of just moving to the nearest integer effectively. If the numbers are big enough, then the assumption is not too bad. And they use finite differences to determine gradients, which is just what we were doing previously. And essentially then their algorithm looks like this. So it will generate some initial booking limits. They'll look at these finite differences, so they'll look at estimates of the gradient, move to a new solution, make that solution feasible, because you want, in the airline problem, there's lots of various constraints. They will need to then make it feasible. And then if no more improvements are possible, or you've got to the maximum number of iterations, they'll stop and return the answer. Otherwise, they'll go back to 2 and move to another solution, make it feasible, kind of run the simulation with it, test what's going on. If it's satisfied the stopping criteria, they'll go, and otherwise they'll return an answer, and otherwise they'll keep going. And so your algorithm, it's using this stochastic approximation idea on a very different problem that is not obviously stochastic root finding like we were looking at before. It's also multi-dimensional as well, which makes it that bit harder to solve. So it's a bit of an aside, just to give you a very different example of where simulation optimization could be used, but also hopefully of interest. And this part here, this 2 and 3, is the stochastic approximation part. Okay, that ends what I will say about stochastic approximation. So my last couple of slides are just on heuristic methods. So heuristics are not exact methods of optimization. There's no guarantee you will find the exact optimal value. Instead, they are using some understanding of the problem and the structure of the problem to move towards a good solution. So, if everything went to plan, they would find that optimal solution, but there's no guarantees or anything that they will find that optimal solution. It covers a very broad range of optimization algorithms, but most of them that you see in the literature, I think this is fairly true, in simulation optimization, are based on the principle of random search. So you are, in some ways, searching in a structured way through your decision space. Random search methods have the following characteristics. So the first thing, decision variables x are generally not continuous. So you are looking at discrete values for x. And the example we had was the number of call handlers in a call center. So how many people you have employed answering telephones in a call center might be a good example of a decision variable. And it might be that you have call handlers that can answer this particular query and another set of call handlers that can answer a different kind of question, and you're trying to decide how to balance between them, for example. So your decision variables x are then not continuous, but you have got some idea of how they relate to each other. Number of feasible solutions is generally large. So, for example, say greater than 20. You could go higher than that. There will often be very large problems. And so essentially it's not feasible to sample all of them. What you find then is the algorithm moves around the decision space in a random fashion, and the randomness is important because that stops you getting stuck in these local minima. So we talked a little bit about local minima just a moment ago when we introduced those nasty functions in the stochastic approximation example. This case, you will also have functions which have dips in all sorts of places, but what you want is the one with the biggest dip, so the minimum, global minimum, if you can. And you want to stop your algorithm getting distracted by these smaller local minima. And so adding a certain random element to it will allow it to jump out of these local minima if it's beginning to get stuck. So in general, in each iteration, the algorithm will sample points from the neighbourhood of the current point. And this is where understanding the structure really helps with getting the simulation optimization method to work well. Is how you choose that neighbourhood can be quite important and can be quite dependent on the structure. If the output at a sample point shows sufficient improvement, then the algorithm will move to this point. So we come into ideas and algorithms like simulated annealing, for example. So has there been enough improvement? Yes, well, I will move to that point then, or no, or maybe it's not better, but I'll move to it with a set probability. So there's randomness in the algorithm as well as randomness in the output. As I said before, the neighbourhood of a point x is the set of possible values that could be sampled when choosing the new point x prime. So when you're looking at where you're going to test out next, it's the values that are around x. Now, what that around x means in the context of your model will depend on what you're actually modelling and what these decision variables represent. But if we think about the call handlers example, then maybe the neighbourhood of x would be one more call handler of this particular type, one less call handler of that particular type, one more of another type, one less of that type, etc. So you're looking at solutions that are close. So that is, as I say, there's so much to say on this, but the reason I haven't put a huge amount in here is that quite a lot of these heuristic methods are not hugely different when you look at them in a simulation output perspective as when you look in a deterministic perspective. Is that true? I think that's reasonably true. So you do need to account for the uncertainty, but in some ways, because they're heuristics, you've almost got that you're building them for the problem, and so they're set up almost for the problem. So the key thing to remember is accounting for the uncertainty and making sure that you've got some way of doing a final check on your solutions that they are actually giving you the best values. So I will finish with this this summary of the talks that I've given this morning and tutorials I've given this morning. So a few things just to say. So the first one is simulation optimization methods can be used in real simulations. So that's the point to emphasize really. Although we've shown you examples which are toy models that we kind of know the answer to, they can be applied to real simulation models. You can build yourself an agent-based model using the tools that Stefan showed you yesterday, and then decide that you want to find the best parameter for one of those. So what's the best parameter for this particular simulation model? I know I will go and run a simulation optimization method to do that. And actually, having done everything in Python, that becomes a lot more straightforward to do. One thing you should do before setting up the optimization and designing the study is just define your problem. So write it down. What is my objective function? What are my decision variables? What do they look like? Have I got an infinite number? Have I got are they on continuous space? Are they discrete? Are they more like categorical variables? How do I define it? How do I classify my problem? And at that point, you can then get to choose your method that you want to use and the method that's most appropriate. So a final point on this, on the what you should remember, if you can't easily communicate with your simulation model, for example, you've built it in a package and the code doesn't connect up with it easily, there are two-stage procedures, and boot comp is one of them. So boot comp, I don't think I've put the link on the slide, have I? No, is a method that Tom Monks and I, so Tom was the other person who put that optimization tutorial together. We developed this method as a two-stage method to carry out ranking and selection problems. The reason being that often if you're using a package for simulation, then you won't be able to communicate with it after every run. It would just get too complicated and time consuming. In which case bootcomp will do an initial set of replications and then tell you how many replications to make for each of your systems in the second stage, and it uses bootstrapping, which is why it's called bootcomp. So that's another thing that you can consider. I also wanted to emphasize what I missed. So this has been a morning in my time or an afternoon in your time of looking at simulation optimization. I haven't covered everything. There is a lot of other work out there. What did I miss then? So one thing that's a reasonably big area at the moment is the use of cloud computing and parallelization to speed up simulation optimization methods. So you can have your simulation running in lots of different threads on your computer and get the results back. You've then got the problem of how often you join up those threads to talk to each other to decide what to optimize next. And there are methods being developed that do that. So that's quite an interesting development, and one that certainly be useful for when we're looking at things like real-time simulation optimization, where we're looking at running the simulation and the optimization very quickly to inform what the system should do next. So that's certainly something that's new at the moment. Another key thing which again makes the optimization more difficult is multi-objective optimization, and this is where you have more than one objective function. So you might, and this is something we're looking at in the disaster relief project that we're working on, you might want to minimize the response time in getting to someone with relief food, for example. You might want to get there as quickly as possible. But you also have a secondary objective, which is cost. So you also want to do that in the cheapest way possible. So you've got these often competing objectives here. One may be more important than the other, and you can take account of that. But having both of them in your head or both of them in your model is quite important. So multi-objective optimization will allow you to take account of several different objectives at the same time. Now, we did touch a bit on subset selection because we talked about OCBAM, but there's more to say on that. So, but I think we've seen that at least, so we know it exists. The links with statistical learning are quite interesting, and there's work, for example, multi-armed bandits, if you've heard of multi-armed bandits methods. There's quite a lot that you can learn from statistical learning and employ in simulation optimization. They follow quite similar patterns. And so there are certainly some good books there which you can actually download for free, which are worth looking at to learn more about statistical learning, and that will help with the optimization. So another thing that is happening more and more now, particularly with these fast return simulation optimization studies, so where you want the answer back very quickly, is to use what's called multi-fidelity optimization. So here you will have a simple model that describes the output of the simulation. It may just be a statistical model that you fitted previously. So you might do an overnight fit to the simulation to get this kind of simple model that can return answers very quickly. So then when you need an answer, you'll run that simple model, and that will say, well, I think these 5 solutions look like the top 5. And then I can run them through my simulation to get to what the actually which one of these looks to be the best. And that helps you get to the answer quicker, because often running the simulation can be a really slow process. So multi-fidelity optimization is something else that's being thought of at the moment. And then I put it at the end, but I've mentioned it twice already, this real-time simulation optimization is getting answers back quickly. Is obviously really important. A few resources then at the end. So that's my email address here at Southampton. Tom Monks, if you wanted to contact him, particularly about sim tools, which we used previously, that's his contact email address here. The GitHub link for the sim tools package, if you were wanting to look at that and find out a bit more about it, I've included that here. If you're looking at simulation and want to do more in simulation, and particularly in this kind of analysis of simulation models, I would really recommend the Winter Simulation Conference archive. So they have all their papers in that archive going back, I think, probably at least 20 years, but maybe even further than that. And they have amazing tutorials in there, tutorial papers. And these are really worth looking at. So you'll often find some very good papers on input analysis or simulation optimization tutorials in that Winter Simulation Conference that are well worth a look and a read, and will really help you get started with some of these ideas. The other aspect, other book that I think it would be worth, that I have used extensively and is worth reading if you can, although I don't think there's an electronic copy available, is the Handbook of Simulation Optimization by Michael Fu. And that introduces in different chapters all the different methods that we've seen today, and also a lot more besides. So that's also a good book to use. Great. Right, I will finish there. So as I say, time for questions. So I've allowed some time for questions before we finish off the workshop. I can see 2 in the chat. I'm going to stop sharing now so I can keep a better view, and let's have a look. So Christine, in statistical approach, can we often, what the multivariate analysis will often do is say, here's the output of all my simulation methods, all my simulation runs. Let's do some statistical analysis on it and find out what's going on. So what's the, you might be looking at which one is clearly the best, or you might be just looking at what different input parameters, what the effect of different input parameters were on the outputs of your simulation method model. And that's a really interesting study. What the simulation optimization methods will try to do is to try to focus where you place your replications. So you will often do, the simulation optimization will say, actually, you don't need to try in this area anymore because we know that's not likely to be very useful. Kind of focus a little bit more on this particular area of the decision space because there's more to find out here, and this looks like where we would want the real system to be running. But once you've done that and you've got all this data, then yeah, definitely multivariate statistical analysis is really useful for kind of analysing that output. Also, if you understand those methods, it makes it easier to understand what the optimization methods tend to be doing. So yeah, no, that's a really good point. I don't understand the next question, unfortunately, so I will keep, and I'm not even going to try to translate it because my Indonesian is not brilliant. So
it's not a question, Christine. It's a comment.
That's fine.
Yeah.
Good. Okay. Any other questions at the moment? Otherwise, I will hand over to Stefan. Okay, I will say my thank yous for thank you for listening. Thank you for putting comments in the chat. Thank you for asking questions and for participating. It's been lovely talking to you. As I said, I wish I could be there and talk to you directly, but there's a lot of things we wish could have happened over the past 2 years, which haven't for the whole world, I think. So thank you ever so much, and I will hope to meet some of you at some point in the future. I think that's all we can say. I will make sure that my slides, I think I've sent my slides to Stefan, so hopefully you can get a copy of those afterwards if you're interested. But great, I will hand over to Stefan now. So I think he's finishing off.
Bu Ismi, acara berikutnya.
Okay, thank you very much, Professor Christine, for answering this question and also for the exercises and great presentation. It is a pleasure to have you with us.